Our lecture today will be about the behavior of errors. We're going to get suspicious. So we're going to consider that we can't obtain the true value of any variable due to the existence of errors. And what we can get is what we call the most probable value, القيمة الأكثر احتمالا, or what we call the best estimate. We can try to improve the accuracy of the most probable value by various conditions. One is to measure several times, as to measure 10, 20, 30 times. As we obtain more observations, we can improve the accuracy. We can use better or more accurate instruments by calibrating the instruments and using high accurate instruments, or by using experienced observers. More experienced observers will produce more accurate results. So we said that we have errors, so we need to know what are the sources of errors and what are the kinds of errors. Sources of errors are mainly due to natural conditions or atmospheric condition or the surrounding environment itself, such as the temperature and the pressure and the humidity and earth curvature. And if you're mounting the instrument on a moist ground, then it could settle by time. The second source of error is the instrumental errors, which is due to the instrument or the device you're using. For example, if you have a missing part of any tape, or the index error, or the axes of the instruments are not perpendicular to each other. And the third source of error is personal errors, and these are various errors due to the person himself or the observer himself. For example, imperfect pointing, pointing to a different point, not holding the staff vertically, the horizontality or the plummeting of the theodolite or the total station is not perfect, and so on. So these are the most common type sources of errors. So we basically spoke about different sources, which are natural, instrumental, and personal errors. We'll move on to the kinds of errors. So we know now the sources of errors. We need to know how to classify them. First, there are the blunders or the bloopers or the mistakes. These are odd values, unrealistic values, mainly because you didn't hear properly, or you forget something, or you wrote something wrongly. So the mistakes are because of what I said, is usually a personal error. For example, if you write something wrong, if you point at A instead of B, if you forgot to fix the horizontality from the start, these are mistakes. And they are huge. They should be huge and odd value. Secondly, the systematic error, الخطأ المنتظم. Systematic errors, and because it's called systematic, it's usually the source of this error is usually instrumental, because in order an error to be systematic, three factors has to be valid. Number one, it has to be repeating. Number two, it has to have the same sign or the same direction. And number three, it has to have the same value. So if it is one time it's positive and the other is negative, then this is not called a systematic error. Example for it, if you have a cut at the start of any tape, or you're given a benchmark of 10 meters instead of 9, index error, is also considered a systematic error. The third type of error, which is the most common, is the random error, الخطأ العشوائي. And because it's called random, we don't know a lot about it. However, we know some properties of this error. It's the error appears in a non-organized manner, and unfortunately it doesn't follow any criteria or habit, but you can't expect its value, but you can, and you can't remove it, but you can try to minimize it as much as possible. And because it's a random error, then the probability of having negative errors is the same as the probability of having positive errors. And because it's something unmeant and unintentional, so the probability of large errors is small, while the probability of small errors is large. They will exist in any surveying operation, and they will be large in number, but the value of them is small. And because of this criteria, then they tend to cancel each other, and they should follow after large number of variables and observations. Then they should follow the Gauss probability distribution function. Example for that is if you have a closing error in the leveling procedure or in the traverse observation. These are some examples of the random errors. After we knew about the source and kinds of errors, then we should know how to treat these errors. So we have three types of errors: the blunders, the systematic, the random errors. The blunder, as we mentioned, it's an odd value, so we have to get rid of it completely. Exclude it from the measurements, remove it, delete it, and don't use it. And so you can spot it easily because it's an odd value. The systematic error, because of its property, then you can model this error by using a certain observation procedure like the face left and face right in the theodolite, or by using a mathematical model like the index error, or by calibrating the instrument from the start and using the instrument properly. The random error, what we can do is we try to minimize this error by using what we call the theory of errors. However, in order to apply the theory of errors, you always need to remove the blunders and systematic errors before using the theory of errors in order to properly try to minimize the random error itself. Theory of errors. So we're going to deal now with the random errors. We're going to give an example of, say we have a length L measured n times. So how are we going to get the most probable value of this variable L, which we call the L bar? Basically, we have what we studied before, the arithmetic mean. We're going to sum up the variables or the measurements and divide by the number of measured times. However, this value is actually is not giving any idea of how accurate are the results. Because if, for example, if we have three measurements, 90 and 100 and 110, then the average value will be 100. But you have and if you have the same variable, but you measured 99 and 100 and 101, then the average value will be 100 as well. But the first example, the measurements are far from each other, while the second measurement, the variables or the measurements are close to each other. So in order, if we have a variable and we measured this variable more than or n times, how to obtain a measure for the precision, or let's say for the accuracy for now, we're going to calculate what we call the residual, الخطأ المتبقي, V. V is simply calculated by subtracting the value of, or subtracting the average value or the arithmetic mean from each observation. So if you have 10 observations for the same variable, then you will have 10 residuals. Each one will be the average value subtracted by the observable or the measurement itself. And then we can use it to draw what we call the histogram of error. This is a very good habit to do, is to do some checks. The first check is due to this equation, then if you summed up the whole residuals for all measurements, then the sum up the summation will be equals to 0. And this is because the average value is always a mean value. Some of the measurements will be greater than, some of the measurements will be smaller than. So when you sum up the residuals, they should, whatever the measurements are, this is a calculational or computational check. So in order to see how do we deal with the equal weight univariate statistics, equal weight because it's you didn't weigh any variable or any measurement other than the other, and univariate because we're dealing with only one variable. So if we measured n times, and we can draw the histogram of errors. Here I set the interval, and here I set the frequency of occurrence of this error. Basically, this is the error that is from 0 to 1. How many times did this V occur? Then it say 100 times. From 1 to 2, how many times did this variable of this error occur? Then it's 70 times, and so on. From this histogram, you can see that the probability of small errors is large, the probability of large errors is small, and it's almost symmetric because the average value is within the mid value, and some of the errors are greater and some of the errors are smaller. So this is basically what we're starting to do about how to calculate the arithmetic mean or the most probable value for any variable that say length in this example measured n times. What happened if we theoretically, not practically, theoretically, we measured not n times, but n is very, very large, tending to be infinity. Then we will have lots of values. Then the intervals, we can decrease the interval itself, and the most probable value will turn into the true value because we measured infinity times, and the residuals will be called the true error, epsilon. And the histogram is turned into a curve. The histogram, because you decrease the intervals, you have lots of measurements, then the histogram is turned into the probability normal distribution function of Gauss, which has several properties. Mainly, it is bell-shaped. The area under the curve is 1 because the probability of having all errors is 100%. It's symmetric because some errors are positive, some errors are negative. It's maximum at epsilon equals to 0, and it's parallel to the x-axis at plus or minus infinity, because as the errors gets larger, then their probability is very small. Let's go now to the standard deviation. The standard deviation is a measure of precision, and now we're going to differentiate between precision and accuracy, and I will stress on precision, and then I will mention the difference between the precision and accuracy. Standard deviation. Standard deviation sigma, what we call in Arabic is الانحراف المعياري، معيار لمدى انحراف الأرصاد عن القيمة المتوسطة. This is the definition that you can understand what we call the standard deviation. Why do we use the standard deviation? Because there's lots of different measure of precision. For example, the probable error, the average error. But the standard deviation is the best measure of precision. Why? Number one, because it has geometrical interpretation. If you draw the probability normal distribution function and say you have a very large n, it should be theoretically infinity, but I'm going to assume that we have only 100 measurements for this single variable. Then if you calculated the sigma, the standard deviation for these measurements, then you will find that any curve will have two inflection points, نقط انقلاب. It's actually the point where the curve turns from concave to convex. These two inflection points will happen at a value which is usually or has to be equals to sigma. So basically, if you have 100 measurements and you calculated and say it's a length L equal whatever in meters, and you calculated the standard deviation as we're going to see sigma by say it's going to be equal 2 centimeters, then you will find that these two inflection points happen at a value of V, which is positive or negative, at a value of V equals to 2. So it has a geometrical interpretation ليها معنى هندسي من نقطتين الانقلاب دول. Secondly, why the standard deviation is the best measure of precision? Because you will find always a fixed ratio. If you measured 100 times, then you will find 68% or 68 measurements of the total 100 lying between plus sigma and minus sigma, or say for our example here, plus 2 centimeter to minus 2 centimeters. If you get 95 of these 100 measurements, you will find them lying between plus 2 and minus 2 sigma, from 4 centimeters to negative 4 centimeters. And 99 of these 100 measurements, you'll find them between plus 3 to minus 3 or plus 6 to minus 6 sigma. And from this, we can say that measurements lying between plus sigma to minus sigma are called good observations. Minus 2 to plus 2, we call them bad observation, and minus 3 to plus 3, we call them very bad observation. You obviously notice that it's not 100% because the 0.3% remaining at the far most positive and negative values are the mistakes. Thirdly, why do we use the standard deviation as the best measure of precision? This is because it magnifies the error. Standard deviation is calculated by square root sigma b squared over n minus 1. So we're going to get the residuals for all measurements, square them, and then sum them together, and then divide by the number of measurements subtracted by 1. This is what we call the standard deviation of single observation. دقة الرصدة الواحدة من المية اللي احنا رصدنا. So you can see that we're magnifying the error. The squaring magnifies the error, so you can spot them easily. So large errors will be enlarged. The best example for this is if you have a square, if you're squaring 2, then it's 4, but if you're squaring half, it's quarter, it's 0.25. This is what we call the standard deviation of single observation sigma x, and there's other naming for it. We call it the accuracy of the instrument, or standard deviation of the instruments, or accuracy of the observer, or mainly the precision of the observers. In order to calculate the standard deviation of the mean, not the single observation, if you measured 100 times, then this is the standard deviation of each measurement. But in order to calculate the standard deviation of the mean, then you add n. So basically, the sigma x bar, the standard deviation of the mean, equals square root sigma b squared, the same thing, over n minus 1 over n. And this is the standard deviation of the mean, or sometimes we call it the mean square error or the standard error. Easily, you can now figure out that sigma x bar equals sigma x over root n, which we added here. And this is a very important equation because for example, if you're measuring a distance with a tape of accuracy 1 centimeter, tape is the minimum measurement on it, or the minimum division on it is 1 centimeter, and you want to get you want to measure a distance, or this distance, with a precision of 0.25 centimeter. How you're going to achieve it? Then you're going to say, I'm going to use this tape, measured this distance for whatever number of times in order to achieve the precision that you want from me. Also, you have to note that since we said that 3 sigma is the maximum we can get, if you have a mistake and you didn't spot it, and you found a residual that is greater than 3 sigma, the single observation, not the mean, then you have to exclude this residual and recalculate the whole mean again. Furthermore, we're going to use sometimes the standard deviation, and we're going to use the squaring itself. So just for a naming, the squaring is called the variance. Also, it's very obvious that usually or always the standard deviation of the mean is smaller than the standard deviation of a single observation due to measuring n times. In order to easily understand the whole situation, these are four graphs of measurements, and we want to compare between these four probability normal distribution function. You can see that from number one, it's the best, the most accurate curve, because the probability of small errors is very large. Probability of large errors is very small, and we have no big or large errors. However, in the second graph, the blue one, it's less accurate because the probability of small errors decreased and the probability of large errors increased a bit than the black one. Regarding the red one, it's less accurate, because now the probability of small errors is usually equal to the, or almost equal to the probability of large errors. And number four is a very good curve, but unfortunately you didn't remove something here, which we can say it's the systematic error. So you're getting a very good curve, but it's not correct because you didn't remove the systematic error from the measurements before applying the theory of errors. At the end, as I mentioned earlier, we want to find or to determine the difference between the precision and accuracy. So it's you have to differentiate precision، الدقة، بني آدم دقيق. Accuracy، الصحة، بني آدم صحيح. So how to determine this measure of errors? It's easy to differentiate now between the precision and accuracy. Precision, it is a degree of closeness of repeated measurements to each other. We call it internal consistency. مدى تقارب الأرصاد من بعض. Accuracy is the degree of closeness of repeated measurements to the true value. We call it external, measure of external consistency. مدى تقارب الأرصاد بالنسبة للقيمة الحقيقية. And after defining these two measure of errors, you can always say that we're measuring the precision, not the accuracy. Why? Because we don't know the true value. Given an example from true life, if you're going to do some, or to play darts, and if you can see these four figures, this is a person. If he's playing darts and he got these results, then he's accurate and precise. Why? Because the measurements are close to each other, but and also it's accurate because it's in the yellow proper mid-center. This player is very precise because the measurements are close to each other, internal consistency, but it's far from the true value. This is accurate because it's around the true value, but they are scattered, they're not close to each other. And this is inaccurate and imprecise. So basically, we're always measuring the measure of precision, not the accuracy. When you will determine the accuracy, if you know the true value. This is the only way you're going to know which measurement or which observer is accurate or not, by knowing the true value itself. At the end, a very important factor that we need to know is the relative error. The relative error is very useful when you're comparing the precision between two quantities of different physical units. If you have someone who measured a distance and someone who measured an angle, and this got a standard deviation function of the distance and this got a standard deviation function of the angle. For example, if one measured a distance of 100 meters and got a standard deviation of 1 centimeter, and one measured an angle of 60 degrees and got a value of 3 seconds, how are you going to compare between these two variables, then you will divide the standard deviation by the value itself, and you'll get the relative error. You'll get something with no units, it's unitless, and as this number gets smaller, then you are better. Or you're comparing same units but different magnitude. One measured a distance of 100 meters and got an error of 1 centimeter, and one measured a distance of 500 meters and got a distance of 3 centimeters. How you're going to say who is more precise? By dividing the standard deviation over the value itself, and thus you will determine the relative error. Example, if you have someone having a relative error of 1 to 10,000 and one having a relative error of 1 to 8,000, then the 1 to 10,000 is more precise than the one with the 8,000, because he will have an error of 1 in every 10,000 measurements. On the other hand, the other person will have an error of 1 in 8,000 only measurements. Thank you.